Everybody keeps talking about AI tokens. This model has a 200,000 token context window. That service charges by the token. You've used too many tokens. Your response was cut off because you ran out of tokens. And if you're a normal person, you may be reasonably wondering, what is a token? Is it a word? Is it a letter? A sentence? Some kind of tiny cryptocurrency being mined inside my laptop? Although, honestly, tiny imaginary currency that disappears every time you ask a chatbot a question is not the worst description I've ever heard. The basic pieces of language that large language models process. They help determine what an AI can read, what it can remember, how much it costs, and sometimes why it produces such strange answers. But a token is not exactly a word. It's not exactly a character, and it definitely isn't a thought. So let's take the whole thing apart and see how it works. Hey, I'm Mike, and this is Seasoned.Tech, AI and technology for people who remember dial-up. Today we're talking about LLM tokens, what they are, how they're created, what happens to them inside a large language model, and why any of this should matter to you. Because tokens sound like one of those deeply technical details you should be allowed to ignore. And honestly, most of the time, you just can. You don't need to understand internal combustion to drive to the grocery store. But if your car starts making a noise like someone put silverware in the engine, a little understanding suddenly becomes useful. Tokens are kind of like that. Understanding them helps explain context windows, AI pricing, slow responses, forgotten instructions, mangled spelling, bad math, and why an AI can sometimes write a decent legal drama but struggle to count the letters in a word. So let's begin with the most important point. Part one, a token is not a word. When humans look at a sentence, we naturally see words. So, for instance, take this sentence. The robot carried the groceries upstairs. Most of us would call it 6 words. But a language model does not necessarily receive those as 6 neat words. Before the model sees the sentence, another piece of software called a tokenizer breaks the text into smaller pieces. Those little pieces, those are the tokens. Depending on the model's tokenizer, a common word like the, T-H-E, might be 1 token. Longer word might be split into 2 or 3 tokens. Punctuation can become its own token. Space, it can be attached to the beginning of a token. A number might be broken into several pieces. And an emoji can use more tokens than seems morally defensible. The exact result depends on the tokenizer used by that particular model. That means there is no universal rule saying 1 word always equals 1 token. A useful rule of thumb for ordinary English is that 1 token averages about 4 characters, or roughly 3/4 of a word. So 100 English words might become somewhere around 125, maybe 150 tokens. But that's an estimate, not a law of physics. Unusual names, technical terminology, foreign languages, random strings, and emojis can produce very, very different results. The phrase artificial intelligence might be divided into familiar pieces that the tokenizer recognizes easily. A rare medical term, however, could be chopped into several smaller pieces. A password that looks like somebody sneezed on a keyboard might become a small parade of individual tokens. Why does this system do this? Why not just use the entire word, right? Because there are far too many possible words. English already contains hundreds of thousands of them. Then we have names, slang, spelling mistakes, product names, abbreviations, compound words, and every new term the technology industry invents because it got tired of the old terms. If every possible word required its own permanent entry, the model's vocabulary would become giant, and it would still fail whenever it encountered a word that it had never seen before. On the other hand, the model could process text 1 character at a time. That would let it represent any word, but sentences would become much longer sequences. The model would have to do more work to understand that the characters C and A and T together form the word cat. Well, they're the compromise. Frequently used chunks of text, whole words, parts of words, punctuation marks, and other recurring patterns. Think of a tokenizer as like a warehouse manager packing language into standardized boxes. Right? Common items fit neatly into one box. Items require 3 boxes, some tape, and an employee who's questioning every career decision that led to this moment. How tokenization works. A tokenizer usually begins with fixed vocabulary. This is not a vocabulary in the human sense. It isn't a dictionary containing definitions. Closer to a catalog of text fragments the system knows how to represent. Each fragment has a identification number. For example, imagine a tiny, completely fictional tokenizer. The token for "the" might have the ID number 412. The token for "robot" might be 8,007. The period might be token 13. These numbers are examples, not the real IDs from any specific model. The important point is that the model does not receive the sentence as ink on a page. It receives a sequence of numbers. "The robot stopped" becomes something like 412, 8731, 2916, 13. I mean, again, those numbers are imaginary, but the process itself is real. The tokenizer converts text into token IDs before the language model processes it. When the model produces an answer, the process runs in the opposite direction. The model generates token IDs, and the tokenizer converts those IDs back into text that we can read. This is why people sometimes say an LLM doesn't really see words. That statement is broadly useful, although technically it can become one of those arguments that traps like 6 engineers in a conference room until somebody turns off the lights. The model receives numerical representations of tokenized text. It learns relationships among those representations. It does not experience a sentence the way you or I do. It has no little reader inside it sounding out the words. There is no tiny professor sitting in the server saying, yes, a metaphor. But there is math, a lot of math, a spectacular amount of math. Tokenizers are usually built by analyzing huge collections of text and finding useful recurring patterns. Common combinations can become individual tokens. Less common words can be assembled from smaller pieces. This allows the system to represent words it did not store as complete units. So let's suppose the tokenizer has learned pieces resembling un, un, and able, able. Well, it might be able to construct unbelievable from those pieces, even if the full word is not represented as one token. Now, different models use different tokenization systems and different vocabularies. So the same sentence can use a different number of tokens depending on the model. This matters if you're estimating costs or trying to fill a large document inside a context window. Token count from one model is not automatically the token count for another. From text pieces to meaning. Once the tokenizer has converted the text into token IDs, the model needs a way to do something useful with them. So an ID number by itself, it has 0 meaning, none. If the token coffee, COFFEE, is assigned the number 9416, the number 9416 does not naturally contain the aroma of coffee, the concept of breakfast, or the knowledge that drinking 6 cups before a meeting may be a tactical error. It's just a label. Now, inside the model, each token ID is mapped to something called an embedding. An embedding is a long collection of numbers, or a vector, that represents learned features and relationships. You can think of it as a set of coordinates, an enormous mathematical space, just gigantic. Tokens used in similar contexts develop representations with useful relationships. E may have relationships to words involving drinks, caffeine, bugs, and my ability to behave like a member of society before 9 o'clock. The model learned these relationships during training by processing an enormous amount of text, repeatedly adjusting its internal numbers. Nobody sat down and manually told the model, coffee goes here, tea goes over the screwdriver, closer to tool, unless we're discussing cocktails. The relationships emerge from patterns in the training data. The model also needs information about order. The dog chased the robot does not mean the same thing as the robot chased the dog. The tokens are nearly identical. Their positions are different. So the model incorporates positional information that helps it track where tokens occur within a sequence. Now it has numerical representations of the tokens, information about their order, and layers of learned mathematical relationships. This is where the transformer architecture begins doing its work. The key mechanism you'll hear about is attention. Attention lets the model weigh relationships between tokens in the current context. In the sentence, Mike put the laptop in the bag because it was raining. What does it refer to? The laptop, the bag, the weather? You and I use context to make a judgment. The model uses attention patterns and everything it learned during training to calculate which relationships are most useful as it processes the sequence. Attention is not the same as human attention. The model's not concentrating harder or becoming emotionally invested in the bag. What it is a mathematical operation that helps determine how strongly different token representations should influence one another. This happens across many layers with many attention patterns working all at once. By the time the information passes through the model, the representation of each token has been influenced by the surrounding context. That is one reason the same word can function differently in different sentences. Bank, besides river, develops a different contextual meaning than bank beside mortgage. Same spelling, potentially the same initial token, different surrounding tokens. Context changes the representation. The next token machine. Now we reach the part that makes the entire thing work. A large language model generates text by predicting the next token. That sounds almost insultingly simple. I mean, you type the best way to make a grilled cheese sandwich is ... The model analyzes all the tokens in the conversation and it calculates a probable distribution over the next tokens that could come next. It's a high probability. Buy is another possibility. Maybe it decides the next token should begin a detailed lecture about butter. One token is selected. Then that new token is added to the sequence and the model predicts the next one. And then the next one. And then the next one. The entire confident-looking paragraph appears through repeated prediction. It doesn't normally write the complete answer somewhere in a hidden document and then paste it into the chat. It builds a token by token. This is why you can watch the words appear. Also, why stopping generation early actually stops the model. The remainder of the response may not exist yet. Calling an LLM autocomplete is both technically enlightening and deeply misleading. Your phone's autocomplete might predict the next word in a text message. A modern language model is performing a vastly more sophisticated version of next token prediction using enormous learned representations like attention, long context, and billions of internal parameters. The basic objective is simple. The system built around it is not. It's a little like saying a symphony orchestra creates music by moving air. I mean, it's true, not the entire story, though. During training, the model saw sequences of tokens and learned to predict missing or subsequent tokens. When its prediction was wrong, the system adjusted the model's parameters ever so slightly. Repeat that process across a colossal amount of material, and the model becomes remarkably good at continuing patterns. Now, those patterns will include grammar, style, programming, associations, argument structures, jokes, formats, many sorts of reasoning represented in text. But there is an important consequence. The model's fundamental job is to generate a plausible continuous goals. They often overlap. A truthful answer is usually a plausible answer. Not always. If the model lacks reliable information, it can still produce tokens, forming a confident, polished, completely fictional response. This is what we call a hallucination. The model is not necessarily trying to deceive you. It is doing what it was trained to do, continuing the sequence. This is why connecting an AI to search, databases, calculators, or even other tools, it can be really, really valuable. Those tools give it access to information and operations beyond the patterns stored in its perimeters. Context window. Tokens also determine how much information the model can work with at any one time. This is called the context window. If a model has a context window of 100,000 tokens, that doesn't mean it permanently remembers 1 tokens about you. It means the model can process up to roughly that amount of context during a particular request. The context may include things, system instructions, your current prompt, earlier messages in the conversation, documents you provided, results returned by tools, and some or all of the response being generated. Think of the context window as a moving truck. Let's do everything you needed for this trip has to fit inside. Your question goes in, the conversation history goes in, the 90-page PDF you uploaded goes in, the AI's instructions go in. And eventually, somebody is standing at the back of the truck holding a floor lamp and saying, this is not going to fit. When the available context becomes crowded, the application has to do something, and it might reject additional text. It might shorten earlier parts of the conversation. It might summarize old messages, or it might quietly leave out information it no longer considers necessary. The exact behavior, well, that depends on the application. This helps explain why an AI can appear to forget something from a much earlier in a long conversation. It may not be a dramatic failure of intelligence. The relevant tokens may no longer be present in the active context. Even when information technically fits inside the context window, that doesn't mean the model will use every detail equally well. You put a critical instruction in the middle of a giant pile of unrelated text, the model may give it less attention than you expect. Humans do this too. If somebody hides the sentence, "bring the fire extinguisher" on page 84 of a meeting transcript, cannot guarantee the refreshments committee will catch it. More context is useful. Better organized context is usually more useful. Tokens, cost, and if you use an AI service through an API, pricing is often based on tokens. So there are usually input tokens and output tokens. Input tokens are what you send to the model. So instructions, conversation history, documents. Output tokens are what the model generates in response. Some services also distinguish cached tokens, reasoning tokens, image-related units, or other categories. The precise pricing changes by provider and model, but the basic idea is straightforward. More tokens usually require more computation. You send a model a 2-sentence question, that is 1 workload. If you send the complete works of Shakespeare, 3 tax returns, a software repository, and the transcript of your family group chat, possibly a cry for help. Longer context can also make requests slower. Every generated token requires another prediction step. So asking for a 5,000 token response generally takes longer than asking for 200 tokens. This doesn't mean you should become obsessed with eliminating every token, though. Some people discover token billing and they begin editing prompts like they're sending telegrams in 1912. Need report. No adjectives. Stop. Clear context is worth paying for when it improves the result. The goal here is not to use the fewest possible tokens. The goal is to avoid wasting them. Duplicated instructions, irrelevant transcripts, enormous unfiltered documents, and endless conversation history can add cost while making the answer worse. Tokenization explains several of the odd things that language models do. First, like spelling and character counting. Ask a model how many times a certain letter appears in a word, and it may get it wrong. Why? Because the model may be processing the word as 1 token or as several chunks, as a clean row of individual letters. Now, modern models have improved at these tasks, and they can sometimes use tools or reasoning strategies or something like that to solve them. But raw tokenization does not naturally represent every character as a separate object. Numbers. Now, a long number may be divided into unexpected pieces. So the model has learned many, many numerical patterns, but it's not automatically operating like a calculator. And that a calculator tool remains super valuable even when the chatbot sounds like it minored in mathematics. Third, unusual names. A common name may map neatly into familiar token. A rare name may be split into several fragments. This doesn't mean the model dislikes your name. It means your name did not win the statistical popularity contest. Fourth, capitalization and spaces. Space Apple may not be represented identically. Okay? Punctuation can change the token sequence as well. So even small formatting changes can alter what the model receives. And fifth, let's talk about other languages. So the number of tokens required to represent the same idea varies across languages and tokenizers. Some tokenizers represent English very efficiently because English made up a large portion of their training material. Now, other writing systems or less represented languages, they may require more tokens for equivalent content. Or multilingual systems can improve this, but token efficiency is not automatically equal across every language. This affects context, capacity, speed, and cost. And window does not translate into the same number of words in every language. So what are you supposed to do with all of this? First, don't treat the context window as permanent memory. If something is essential, include it clearly in the current working context. For a long project, maintain a concise project, bringing important facts, constraints, current states, things like that. That is more reliable than assuming the model will excavate one crucial sentence from 300 messages ago. Second, organize long prompts. Separate instructions from reference material. Use headings. Label examples. Clearly identify the material that you want the model to analyze. Not making a prompt prettier for aesthetic reasons. You're helping the model detect the structure and relationships among the tokens. Third, remove all of the irrelevant information. If you want a model to summarize a contract, it probably does not need the previous conversations about birthday party invitations. Starting a fresh conversation can sometimes produce better results because the model is no longer carrying unrelated context. Fourth, be specific about the output. Say what you want, who it's for, what format it should use, and what restrictions matter. Write something about tokens leaves an enormous range of plausible next tokens. Write a 500 explanation of LLM tokens for non-technical small business owners using one analogy and no equations. Now that narrows the path. Fifth, we use tools when precision matters. So use a tokenizer of the provider's official token counting utility when you're close to a context or cost limit. Use a calculator for arithmetic. Search or trusted sources for current facts. Do not make the language model impersonate every other kind of software just because it speaks confidently. And then finally, don't overthink it. You don't need to count every token before asking ChatGPT where the settings menu went. For ordinary use, mostly, they remain behind the curtain. But now, when an application says your context is full, you know what filled it. When an API bill lists input and output tokens, you know what you're paying for. And when a chatbot insists there are only 2 R's in strawberry, you know there is at least a technical explanation for why the machine has chosen violence. Tokens are the standardized pieces of text that language models process. A tokenizer breaks your prompt into those pieces and converts them into numerical IDs. The model maps those IDs into learned mathematical representations. Then it uses context and attention to relate them to one another. And it predicts which token should come next. And it repeats that prediction until it has built a response. Tokens help define the model's working context. They affect cost, speed, output length, and the way text is tokenized can help explain some of the model's stranger limitations. Remember, a token is not a word. It is not a fact. It is not a memory. And it is not a tiny thought living inside the computer. It is one building block in a system that has learned to produce remarkably sophisticated patterns of language. The impressive part is not that the model predicts the next token. The impressive part is how much structure can emerge when the prediction is performed at an enormous scale. And the caution is that a beautifully predicted sequence of tokens can still be wrong. So use these systems, learn what they're good at, give them clear check important information. And remember that fluent language is evidence of fluent, automatic evidence of truth. I'm Mike, and this is Seasoned.Tech. If this helped make AI a little less confusing, please subscribe to the channel, smash that like button, and let me know in the comments which AI term you'd like me to translate next.